Well, it is almost 9 o'clock. We'll give it one more minute for the last person that's going to try to slip in the door in a hurry. We'll give it one more minute. But go ahead and enjoy today because tomorrow's supposed to dip down again. It's supposed to be like what 77 today or something, but tomorrow it's going to be like 62. So we're doing a lot of this lately. Like our weekend was like two different weekends kind of squished together. We had a beautiful 80-degree sunny Saturday and a rainy 50-degree Sunday, and made those the same weekend somehow. Don't know how that works, but that's what we did. All right, 9 o'clock. Let's get something up on the screen here that's relevant to some algebra. All right, looking on Buzz, going to our grade screen as usual. Let's see where we're at now. Okay, we finished Module 5 a while back in February. We've been doing matrices for a few weeks. Last week, we should have got adding, subtracting matrices. This week, March 8th, we have three things. We're doing the multiply matrices by scalars folder. So everything in that folder. And quiz 1. So you should already have this folder done, adding and subtracting matrices, everything above that, those dimensions, elements, everything like that should be turned in. We just need to do scalars, scalar multiplication, and the quiz. So let's go back and take a look at what that looks like. So scalars, there we go. Oh, wait. Quiz 1. Oh, we have another folder. So look, here's our two assignments. But before the quiz, there's some more lessons we need to go through about the properties just to make sure we understand that. So we've got 5 lessons, a video lesson, and then these 3 lessons, and then the quiz. So we'll go through this, take a look at this, starting with this video lesson right here, multiplying matrices by scalars. And let's see what all this has got to show us here.
Now that we know what a matrix is, let's see if we can start to define some operations on matrices. So let's say I have the 2 by 3 matrix, so 2 rows and 3 columns, and the entries are 7, 5, -10, 3, 8, and 0. And I want to define what happens when I multiply 3 times this whole thing. So first of all, let's get a little terminology out of the way. The number 3 in just the everyday world, if you weren't dealing with matrices or vectors, and if you don't know what vectors are, don't worry about them just now, you would just call that a number, or you would call this a real number. It's just a regular number sitting out there. But now in the world where we have these new structured things, these matrices, these arrays of numbers, we will refer to these just plain old real numbers that aren't part of some type of an array here. We call these scalars. We call this a scalar. So essentially what we're defining here, we don't know, I haven't said what this is actually going to turn out to be, but whatever this turns out to be will be a product of scalar multiplication, or we're multiplying a scalar times a matrix. And so how would you define this? What do you think this should be? 3 times this stuff right over here. Well, the world could have defined scalar multiplication however it saw fit, but one way that we find perhaps most obvious and most useful is to multiply this scalar quantity times each of the entries. So this is going to be equal to 3 times 7 in the top left, 3 times 5, 3 times -10, 3 times 3, 3 times 8, and 3 times 0, which will give us, it didn't change the dimensions of the matrix, it didn't change, I guess you could say, the structure of the matrix, it just multiplied each of the entries times 3. So the top left entry is now going to be 21. The middle entry, the entry in the middle row top column is going to be 15, -30, 9, 24, and 0. So when you multiply a matrix times a scalar, you just multiply each of those entries times that scalar quantity.
That's it. It's that simple. Scalar multiplication. You just actually multiply by the number that's in front of the matrix. So just take each of the elements in the matrix and multiply it by whatever's in front. And while that sounds simple, they're going to try to mix it up and they're going to give us some fractions. But that's not a big deal for us. We can do fractions. All right, let's look at the lesson that goes with the video. Close this little half tab over here. It reviews at first what a matrix is: 2 rows, 3 columns, rectangular shape of arrangement of numbers. But here's what we're going to learn: you can multiply matrices by real numbers. So when we work with matrices, we refer to real numbers as scalars, as he mentioned in the video. The term scalar multiplication refers to the product, which, when you multiply, you get a product, of a real number and a matrix. So in scalar multiplication, each entry is multiplied by the given scalar. So for example, we've got matrix A right here, 10, 6, 4, 3, and let's find 2A, which means we're just multiplying 2 times A. So the 10, 6 is multiplied 2 times 10 and 2 times 6. 4 and 3 is 2 times 4 and 2 times 3. So this 10 and 6 ends up 20 and 12. 4 and 3 ends up 8 and 6. We just simply multiply everything inside the matrix by 2. Like, okay, well, gosh, Mr. Brock, that sounds pretty easy. Absolutely. Let's try it right here. Put this in your chat. I'll open that up. Open up the chat. If we have B, which is right here, and we want to find negative 3B, what numbers do we put in the matrix now? This was our matrix right here. But we're taking that times negative 3. Yeah, really the only tricky part is just paying attention to the negatives, because a negative times a negative is going to be a positive. So when you have a negative 4 times negative 3, we've got to go positive. Negative 2 times negative 3 is a positive. But the second row are positive numbers, so multiplying them will change them to a negative. And that's as simple as it needs to be right there. Absolutely correct. Good job, guys. How about this one? Like I told you, he's going to try to make it a little tricky. Look, 1/3. 1/3. You're like, oh, gosh. Well, that's not as tricky as you might think, because if we have 1/3, that's pretty nice. 1/3, if you have 1/3 x, oh, I guess I should make that not go away. Here, let me change that. We have 1/3 x. If we want x, we just multiply that times 3. 1/3 times 3 is just x. So in this case, since we're trying to figure out 1/3, 1/3 times, down here, negative 42, we can just, well, I was doing the times 3. That was only an equation. We're not equal to anything. So let me scratch that. 1/3 times 42 is the same thing as taking 3 into 40, 42 by 3. Because with 1/3, you're multiplying times the top number and you're dividing by the bottom number. Well, 42 times 1 is just 42. So if we divide 42 by 3, and this is a negative though, so it's a negative answer. Negative 14 would be what we're putting in this box. Negative 14. Sorry with the confusion on the times 3. We'll use that later in the next assignment. So you could also think of it as 1/3 of. What is 1/3 of 27? Same thing as 27 divided by 3, or 1/3 times 27. 1/3 of 27 is 9. 1/3 of negative 3 is negative 1. So different ways to think about that. But that's it. That's as difficult as that is. All right, let's look at the 2 multiply matrices by scalars assignments here. The first one, remember, we're going to turn in the screenshot down below. You want to make sure when you get here that you're logged in up here. If you're logged in, then that helps. It'll keep your score if you forget to take a screenshot. Here's our first question. Find the product Scalar multiplication. Oh, this is great because for this one, we just have a 3. It's like, yay, just a 3. That makes that one nice and simple. 3 times, oh, let's see. I'll go ahead and put these numbers in. 3, 3 times -2, 3 times -1, 3 times 4. It is that simple. Just take all of the numbers in the matrix and multiply them by 3. They do have a calculator if you need that on the assignment here. Show calculator. Okay, there's number 1. All right, try this one. This one, they want us to find the value of x. So x is right there and y is right there. So this is where I was thinking earlier, talking about if you're trying to have an x. Let me see. See if I can draw this a little better. So if we have 1/3, oh, I'm still doing the disappearing ink. Change. Okay. Oh, this is a -1/3. So if we have a -1/3 times x, so -1/3 x equals 2. -1/3. If we want to get rid of the -1/3, we'll just multiply everything by -3. -3 times -1/3 is just 1x. And over here, multiplying 2 times -3 is -6. So that tells us that x must be -6. Because -1/3 times -6, negative times a negative, 1/3 times 6, that would equal the 2 that we're looking for right there. All right. Clear that off there. Okay, the next one is -1/3 times -9. Negative times a negative, it's positive. What's 1/3 of 9? 3. And you can use the calculator if you're like, okay, I'm not understanding this. Well, let's do -1/3 parentheses -1 divided by 3 parentheses. Look, that's -1/3 times, and then we'll take the -9, -9. So we got -1/3 times -9, 3. That's the answer we got. 3. So you can use the calculator if you want to do it that way. That is totally fine. All right, check. There's 2. Find the product. Oh, great. This is just multiplying -2. -2 times -1 is a +2. -2 times 3 is a -6. -2 times 4 is a -8 and a -4. Check. Last question. Oh, this is another x and y, and both of them are in the first matrix. So this says with the x, 3 times x equals -9. If you need to write this down like this to understand it, 3 times x equals -9, and then divide both sides by 3, you're just solving for x. X is -3. If that helps you to write that down, by all means, write that down and solve for x. All right, what is y going to be? I left you the easy one here. What is y going to be? Y is right there. I'll let you look at that. Got you sleeping. What is y? Good pause here because I want to make sure you understand here before we move on. All right. I think you guys are getting this. Yeah. 3 times y equals 6. Love it. So 3. So yeah, if we go, you can work backwards. 6 divided by 3 would be what? It is 2. Very good. Very good. All right. Check. Nice work. Show summary. Oh, look, I caught some confetti. And oh, although I should have scrolled down. I didn't scroll down. Oh, I clicked on something wrong. Okay. Submit. Got all 4 of those right. Okay, this next one's a little different. You might think it's the same. It's like, oh, this again is scalar multiplication. But we're taking it up a notch. If you look at this, let's see what they're doing. Close that again. Oh, this was on 4 of 4. I didn't finish it last time. Look, I've already done 3 problems. We're going to do this last problem here. Okay, what this wants us to do, and this is how these problems are on this one. 3 times x minus this matrix equals this matrix. But x is this. Right? Now let me ask you something. Let me ask you something, because this is relevant. What size is matrix X? Because they gave us a 3 by 3. Is matrix X a 3 by 3 matrix? It shows a 3 by 3, right? 1, 2, 3. Would that work if we make this 3 times and we have a 3 by 3 matrix? And then we're subtracting this 2 by 2 matrix, and it's going to equal a 2 by 2 matrix. Can this be a 3 by 3? That's what they show. Can we do that? Is that legal? How would we subtract this matrix from that? How would we do that? Okay, this is a good review because last week we had cut things short. If you add or subtract matrices, the only way you can do that is they have to be the same size. So this is testing us. This is testing us. We do not need the third row and the third column. X has to be a 2 by 2. These are extra. If you put something there, it'll be wrong because this has to be a 2 by 2 as well. 3 times a 2 by 2 minus a 2 by 2 would equal a 2 by 2. So they're just testing us to see if we know what we're doing. Okay, so to work this problem, because these are a little different than the last one we had. If we're looking at this, it is 3x. And then the first one we're doing is this right here. So that would be the first one right there. Minus 0 equals, what does it equal? Right there, 15. Well, this is just the same as 3x because 3x minus 0 is just 3x. So we just have to divide by 3. So the first element, the first entry there is 5. 3 times 5 minus 0 would be 15. Okay, so the first one wasn't bad. But what about, oh gosh, we got numbers to work with here. All right, let's see again. It's a little easier to write with here. Okay, so if we have 3x, which we have 3x every time, and right now we're doing this one, right? That's the one I'm trying to figure. 3x minus, and we're subtracting a 12. And it equals 42. Okay, see that? I'm gonna erase these so we can see that a little better. So we just need to solve this for x. Add 12. So we've got 3x equals 42 plus 12. Right? Divide by 3. So that means x is 18. 18 times 3 is 54. And again, we don't need that because ours is only a 2 by 2. All right, let's do this one down here now. Let's clear that out. Now we're doing this one, so we need 3x minus 37 equals, it equals 5, right? Because we're looking at this number right here. So we have to add 37 to both sides. 3x equals 5 plus 37. Divide both sides by 3. So this is a 14. Like I say, sometimes it's easier to just get some paper and just write out these little equations. And now we have a very simple Algebra 1 equation. We're just solving for x. Okay, let's do the last one. 3x minus 60 equals negative 30. Okay, so we got to add 60 to both sides. Gives us 3x equals negative 30 plus 60. Divide by 3. So this must be a 10. Okay, we have done all 4. So that means we can turn it in. And look, it's correct. If we would have put anything in this column, either one of those 2 columns, it would be wrong. We can't put something in the 3rd row or the 3rd column. All right. But that's how this one works. Oh, I don't know why my mouse is being funny on me. Okay, there we go. All right, I'm going to go ahead and screenshot that. But that's how that one works is you have that whole matrix you do. It's being multiplied by something. Okay, let's close that. Scroll down. So that's how the scalar multiplication assignment looks. Okay, so we have done all 4 of those. We're going to close that folder. We got to get down to quiz 1. So let's look at these lessons and then we'll look at the quiz. Intro to zero matrices. Intro to zero matrices. Again, it's going to review what a matrix is. It's a rectangular arrangement of numbers. This is a 2 by 3. It has links back to how to add and subtract, how to multiply by scalar, what a matrix is. But let's define a zero matrix now. Just as you might think, you could probably have guessed this. A zero matrix is a matrix in which all of the entries are 0. Wow, Mr. Brock. This is like the duh principle of matrices, right? A 3 by 3 zero matrix, right? If we have a 3 by 3 zero matrix, we have 3 rows of zeros that all have 3 columns. It's all zeros. This is and we label it an O instead of calling it A or B. We label it with a big O. This is an O 3x3. If it's a 2x4, then we just have 2 rows of zeros. So it's like, okay, zero matrices, that seems pretty simple. So we indicate it by the O, and then usually you can put a subscript to let people know how big it is. So zero matrices play a similar role in operations with matrices as the number 0 plays with real numbers. So let's look. What happens when we add a zero matrix? Says, oh, I want to see an example before I practice. No, I think we can go straight to this. Try the following matrix addition problems. We're adding this 2x2 matrix to a 2x2 zero matrix. Remember, they have to be the same size. That's why we're using a 2x2 zero matrix. So what would this be? Here, I'll put that in the chat. I'll give you a moment. What would the new entry be for this matrix right here? What would our 2 rows be for our new matrix when we add the zero matrix? I think you can get this. I've got very strong confidence in you on this one. Yes, Mary, it is that easy. Mary put an answer out there like, here it is. That's it, right? Yep, that's Olivia Owen. Yeah, absolutely. When we add zeros, nothing changes. I mean, this is exactly the same as this. If we would have saw an example, it would have just showed us. Oh, they're showing how to add. That's an example of how to add. We know how to add. That was just showing how to add. But yeah, we just add nothing and we get the same thing. Oh, let's see this one. The 0 is on the left side. Oh, is that going to change anything? Well, gosh, let's see. Is 2 plus 0 different than 0 plus 2? No. It's still all the numbers will be the same. All the numbers, these will look exactly the same. As long as I get all the negatives put in the right place. Okay, there we go. So conclusion. Adding a zero matrix to matrix A and adding A to a zero matrix still just results in getting matrix A as the answer. Doesn't matter. Oh, here's an interesting question. If we want to add a zero matrix to B, here's B. What dimensions will our matrix 0 or zero matrix, how big does it have to be? What are the dimensions of the zero matrix that we're adding to B? Yeah, the only way we can add matrices together is if they're the same size. So it has to also have 2 rows and 3 columns. Good job, Alexander. Pick 2x3. Perfect. Oh, here's something interesting. What happens when we add opposite matrices? So the opposite of matrix A is matrix negative A. Negative A, which means if we have 4 in A, we've got negative 4 in negative A. If we have 1, we have negative 1 over here in negative A. If we have negative 6, we have positive 6, positive 2, negative 2. Try the following matrix addition problems. If we add this matrix to this matrix, what's our solution? What does it end up? What's our answer? We've got matrix A and matrix negative A, which basically means they've taken negative 1 times all of those, like scalar multiplication type of thing, right? Yeah, you got it, Summer. It's zeros. It's a zero matrix. When you add a matrix to its negative matrix, it has to cancel each other out. It's a zero matrix. Perfect. Do we need to go through this one? Negative 4, 2, 5 is being added to 4, negative 2, negative 5. Again, just keep putting zeros, right? Because every number is being canceled out by its negative. I need help. Let's see. Why would someone need help? Oh, they're working through it. Okay. If you didn't know how to do this, you would take 4 and negative 4 and add them together, and that would get you to the zero. So that shows you how it works. So in conclusion, if we add any m by n matrix to its opposite, a plus a negative a, we get the zero matrix. Or negative matrix to the positive matrix. It's a zero matrix. It's also true if we subtract a matrix from itself. A matrix A minus matrix A is zero because that just makes sense. It's like 3 minus 3 equals what? Yeah, it's zero. What happens when we multiply by the scalar zero? 0 times 5, 4, 9, 1. What is 0 times 5? What is 0 times 4? What is 0 times 9? Yeah, I think you have the idea on that. If we multiply by a zero, that's also going to create a zero matrix. Because this works just like normal math does. If you multiply something by zero, you get zero. It's just we have to put it in matrix form because the answer would be a matrix. Zero. All zeros because we're multiplying by zero. Perfect. So any matrix multiplied by the scalar zero gets a zero matrix. In summary, they want to compare it to the real number zero. So in real math, we take a, whatever number a is, and we add zero to it, and we just end up with a. Nothing changes. Which means with the matrix, if we add a zero matrix to matrix A, we just end up with what we started with, matrix A. If we add the negative, you end up with zero. Same thing with matrices. Any number times zero is zero, and any matrix times a zero matrix or times a zero gives us a zero matrix. So that is that lesson. So when you get to the quiz and it asks about a zero matrix, you've got that. All right, let's look at the next lesson. Properties of matrix addition. All right, here are the properties that we're going to look at. The commutative property. This is just like we do in math. A plus B is the same as B plus A. Just like in real math. 1 plus 3 equals 3 plus 1. We know that. 1 plus 3 equals 3 plus 1. It works the same with matrices. If we have matrix A and B and add them together, we can put them in the opposite order and it's still going to be the exact same thing. A plus B plus C is the same as A plus B plus C. That's like if we're adding together 3, 4, and 5, we could take 3 plus 4 and make it 7 and then add 5 and get 12. Or we could take 4 plus 5 and add it together and then add the 3. So it'd be 9 plus 3 would be 12. It doesn't matter if, as long as you're adding three things together, it doesn't matter which two you do first. You're just adding all three of them together. So do them in any order you want to add them first. Okay, the additive identity property. Now, you probably haven't heard the names of these properties in a long time, if you've ever heard. The additive identity property says for any matrix A, there's a unique matrix 0 so that A plus 0 equals A. The identity property says 7 plus 0 equals 7. The additive identity property says 7 plus 0 equals 7. So in matrices, it means if I add a zero matrix to a matrix, it just equals what it started with, the matrix. Then the additive inverse property. It says if I add the opposite of a number, I get 0. 6 plus -6 equals 0. Well, with a matrix, it works the same way. Matrix A plus the opposite of matrix A will give us a 0 matrix. And the closure property. The closure property says A and B is a matrix of the same dimensions as A plus B. See, A plus B is the same as A and B. They all have to be the same size. That's what the closure property says. They have to be the same. If A is a 3 by 2 and B is a 3 by 2, when I add them together, it has to be a 3 by 2. That's all that's saying. That's all that's saying. It has to be the same size. Okay, let's explore this a little bit. Again, it reminds us what a matrix is. I think we got it. To add two matrices of the same dimensions, just add the numbers. 3 plus 5, it's 8. 7 plus 2 is 9. Okay, so that's added. Here's reviews for any of those if you need a review. Now, notice that the sum of two 2 by 2 matrices is another 2 by 2 matrices. So in general, any m by n matrix added together with another m by n matrix will give you an m by n matrix. This is the closure property, which means if we have this matrix addition, we've got this 2 by 3, and we want to add it to this 2 by 2, this is undefined. You cannot add those together. It is not, there's not a way to do that. It is undefined. Okay, so that's the main thing to remember with addition and subtraction, is they have to be the same. Because how would you add them otherwise? What are you adding the 5 to? Are you adding it to the 2, the 7, or the 8? And what about the 7? And so does it work? Let's look at the commutative property. A plus B is the same as B plus A. So if we have 3 plus 5, that's the same as 5 plus 3. Yeah, we know that. We've known that for a long time. So let's look at these two things right here. If we took this matrix and add it to this one, that's the same thing as 3 plus 5, 7 plus 2, 2 plus 8, 4 plus 1. But we could do, instead of 3 plus 5, we could do 5 plus 3. Right? Isn't that the same thing? We just looked at that. 3 plus 5 is the same as 5 plus 3, which means we could have broken it out this way, 5 plus 3. Notice these are the same matrices. They're just in reverse order. But it equals the same thing. They both equal 8, 9, 10, 5. The associative property, A plus B plus C equals A plus B plus C. So right here, doesn't matter which way you do this first, you're going to get 10 on this side, and you're going to get 10 on this side. It doesn't matter if you add these together first or these together first. It equals the same thing. So the same thing with matrices. If I'm adding, oh, these are really small. See if I can make those a little bigger. If I'm adding these three matrices together, I could put these together first and then add the third one, or I could put these together first and then add the first one. But either way, I've got 5 plus 3 plus 1, 5 plus 3 plus 1, 2 plus 4 plus 0. I get the same thing on both ways of doing it. So it doesn't matter if you add 3 together. They all equal the same thing. Just like 5 plus 3 plus 1 equals 5 plus 3 plus 1. All right, the additive identity, a 0 matrix. So I'll make this a little smaller. So when you have a zero matrix added to any matrix, the result's always A. Look at this. Start with this. We add a zero matrix, and it's exactly the same. We have a zero matrix. We add it to this, and it's exactly the same. Nothing changes. Additive inverse. If A is this and negative A is the same numbers except different sign, if we add those together, we get a zero matrix. Okay, check your understanding. For the following problems, let A, B, and C all be 2 by 2 matrices. Okay, that's important. Since they're all 2 by 2, make this smaller. Since they're all 2 by 2, we can do addition. So here, I'm going to look at the chat for this. Which of the following are equivalent to A plus B plus C? So I've got these three matrices, and I'm adding A and B together first, and I'm going to add C to it. A, B, and C, choose all that apply. There may be more than one answer. Tell me which of these is the same as this. Same as that. All right, let's see a couple of folks answering. And remember, basically what we've learned is whatever works with numbers also seems to be working with matrices. All right, I'm seeing lots of folks saying A. Everyone is saying A and B. Oh, and let's see, C. Well, it looks like everyone's saying A, B, and C. So let's say A, B, and C was two. I'm just going to put numbers instead of matrices. So we know if we add those together, we get 10. All right. How about here? If we add 2 plus, and this is B plus C, so that's 8. That's the same. So yeah, I think A works. C plus A. C plus A. So this would be 7 plus B. B is 3. Okay, that works. A plus B plus C. 2 plus 3 plus 5. That's the same. But here we got A plus C. A plus C. That's 7. And then B plus C. And that's 8. That doesn't work because we've added C twice. There's 2 C's in there. So you're right. A, B, and C are all the same. They're all 10. Well, that's a terrible 10. They're all 10. Perfect. Which of the following of these are equivalent, get rid of all this mess, to A plus negative A plus B? And they're all 2 by 2 matrices. That's important in our answer. These are all 2 by 2. A and B are both 2 by 2 matrices. I like this one. Which are the same as the top? Same as this. What do you think? All right, Mr. Brock, you're getting tricky. Now you just have to logic through this. You just have to think about this. If these are all 2 by 2 matrices, A and B are all they're both 2 by 2 matrices. What happens when we add A plus negative A? That's in parentheses. What do you get when you add A plus negative A? And then when you add B to that. When you add B to that. Summer's got a guess out there. Thank you, Summer. I appreciate that. Summer thinks perhaps could it be those two? She's giving it a good guess. I like it. Well, let's think about it. If we add A to negative A, that gives us a zero matrix, right? A plus negative A. So this certainly makes sense. That's what A plus negative A would be, and then we add B to it. So I definitely agree C is correct. But what else is equivalent to that? Could we add the negative A to the B first and then add it to A? Well, yeah, we just looked at a property that said if we got three things we're adding together, it doesn't matter in which order we add them. So yes, B is the same. But what about A and D? Are those the same? What does this equal? If we add a zero matrix to B, doesn't it just equal B? Yeah, we add a zero matrix to A, it just equals B. I mean to B. Add a zero matrix to B, it just equals B. So this one up here is definitely the same as C. This is the only one because we cannot add a 3x2 matrix to a 2x2 matrix. It's the wrong size. It's the wrong size. That one took a little logic, thinking through it. How does this work? But that's right. A, B, and C all work. They all work. Okay, that is the end of that lesson. What else we got left here? Let's see. We have one more, properties of matrix scalar multiplication. Then we're going to look at this quiz. Some good stuff here. All right, close this little half tab. Properties. All right, more properties. The associative property of multiplication, which says if I have three things being multiplied together, C, D, and A, I can multiply C and D together first and then multiply by A, or I can multiply D and A together first, multiplied by C. Yeah, 2 times 3 times 4. It doesn't matter if I multiply 2 times 3 together first or 3 times 4 together first. Either way, I'll get 24. Right. Doesn't matter which way I group that. 12 times 2 or 6 times 4. So this makes sense. Doesn't matter. Let's see. The distributive property, when you have something being multiplied by things in parentheses, you distribute it, right? C times A plus C times B. We do that all the time, distributive property. And you could reverse that and say C plus D being multiplied times matrix A is the same as C A plus C plus D A. I'm sorry, C and D, not B. So the distributive property works the same. The multiplicative identity property. This says, what if I multiply matrix A times 1? Well, what if I multiply 7 times 1? 1 times 7. Well, don't I get 7? 1 times 7 is 7. So 1 times matrix A is matrix A. 0 times A is 0. A number times a 0 matrix is a 0 matrix. Scalar multiplication, 4 times a 0 matrix is still going to be a 0 matrix. And the closure property multiplication says if I multiply a scalar times matrix A, it's going to end up with the same dimensions as matrix A. If A is a 2x2 and I multiply a scalar, the answer is still going to be a 2x2. So that's what that's saying. So let's look a little further in depth here. This reviews scalar multiplication. And if you have a multiplier of 2 out front, you just multiply 2 times everything and end up with that. So let's look at 2 by 2 matrix. Notice that a scalar times a 2 by 2 matrix is a 2 by 2 matrix. Scalars will not change the dimensions. That's what it means by the closure property. Closure property means it's not going to change the dimensions by multiplying by a scalar. So let's look at each property individually underneath it. The associative property. If we are multiplying two scalars, look, we got C equals 2 and D equals 3, right? So we've got a matrix A. So we've got the two scalars in matrix A. We can multiply the 2 times 3 together first and then multiply it by the matrix. We can multiply the 2 times 3 together first and then multiply it by the matrix, which would be 6 times 5. Or we could multiply the 3 times the matrix together first and then multiply it by the 2. Either way, we end up with 2 times 3 times 5 in the final matrix. 2 times 3 times 5. It doesn't matter. So if you're multiplying 3 things together, multiply them in whatever order. Oh, that opens it up for me. Multiply them in whichever order you want to. It does not change. Just like it shows 2 times 3 times 5 is the same as 2 times 3 times 5. All right, distributive property, which we've used in algebra a lot over the years. We just haven't done it with matrices. If we have a scalar and 2 matrices, so we're going to have the scalar times those 2 added together. We can do that. Yep, there you go. 2 times, we can add them together first. 5 plus 3, 2 plus 4, 3 plus 2, 1 plus 6. We can add those together first. And then multiply it times 2. So 2 times 5 plus 3. Or we could distribute it, CA plus CB, because that's the C being distributed. So it'd be C times the first matrix and then C times the second matrix. So you'd have 2 times 5 plus 2 times 3. That's 16, right? 2 times 5 is 10, 2 plus 3 is 16. What is it over here? 2 times 5 plus 3, 2 times 8. That's also 16. Either way, we're going to end up with 16 as our first element. 2 times 6, 12. 4 plus 8, 12. So the distributive property holds true with matrices. You can do it like this, or you can distribute it. And either way, you should get the same answer. So there's the property. Okay, scalar addition. This is having two distributive with 2 scalars in one matrix. We can distribute the A. A is distributed to the C and to the D. So he gives an example showing that. If we have 2 scalars, we can multiply them together and then multiply them by the matrix. Or we can distribute the matrix and multiply each of them individually and then add them together. 2 plus 3 times 6 is 30. 12 plus 18 is 30. 2 plus 3 times 7 is 35. 14 plus 21 is 35. Nice. Works either way. The multiplicative identity product, which means if you multiply by the scalar 1, nothing changes. All right? 1 times this matrix equals this matrix. Because 1 times all of the entries does not change anything. This is called the let's see, where's that? Identity. This is going to be important on our quiz. Identity means you're multiplying by 1. You might write that in your notes. Identity property means you're multiplying by 1. Multiplicative properties of 0. When you multiply by 0, you get a 0. So 0 times a matrix gives you the 0 matrix. My whole computer just totally shut down, which is very, very disappointing because yesterday, actually Friday, he took my computer, totally wiped my computer down to its factory settings and reset it up. And it's doing this again. The computer tech guy is not going to be happy. All right. That was the last lesson. You got the quiz. The quiz is in Buzz. I'm having to restart my computer, so I'll let you guys go. You have the quiz in Buzz to do. It's about all of the stuff that we've already looked at. It should allow some retakes if you don't do well the first time. If you have questions, come see me on Thursday. If any of you grades below 70%, then you're scheduled an RTI for Thursday anyway. Otherwise, have a great week, guys. I'm going to fight this computer soon.